China built a 2,000-kilometer highway across thawing ice. No extra concrete, no cooling machines, no winter delays. Against all odds, the road itself does the cooling. Here's how a highway learned to refrigerate a mountain. At 4,500 meters above sea level, a black ribbon of asphalt cuts across an impossible landscape. The air is thin, the wind constant. The ground beneath has been frozen for tens of thousands of years. But that ground is beginning to soften. Slowly, invisibly, the ice buried under the road is turning to water. And still, the highway does not sink, it does not crack, it does not slide off the mountain. The paradox is strange. The road is warming the world above it, yet somehow refrigerating the world beneath it. How can asphalt cool a mountain? The answer rewrites what a highway can be and what engineering can achieve. To understand the scale of what China attempted, you first have to understand the place, the Tibetan Plateau. The highest, largest, youngest plateau on Earth, covering more than 2.5 million square kilometers. That is an area roughly the size of Western Europe, with an average elevation above 4,000 meters. It holds the sources of the Yangtze, the Yellow, the Mekong, and the Indus rivers of Asia. It has more ice than anywhere on the planet outside the polar caps, the true third pole. Locals call it the roof of the world. Climatologists call it the third pole of our planet. Underneath most of that surface lies permafrost, soil that has stayed below zero for at least 2 years. On the Tibetan Plateau, that permafrost is far older. Some of it is 100,000 years old. Cutting across this frozen ceiling of Asia is one of the most ambitious infrastructure projects of the 21st century. It stretches from Xining in the northeast, past sacred lakes and salt flats, over 5,000-meter passes to Lhasa. For Beijing, this corridor is not just a road, it is a political tendon linking coast to frontier. Since 2000, the central government has poured trillions of yuan into highways, rail lines, tunnels and bridges. Whoever controls movement across the Tibetan Plateau controls water, borders and buffer zones between China, India and Central Asia. But the ground itself refuses to cooperate. What makes it treacherous is not the cold. Engineers build in cold. The real problem is that the cold is not stable. Permafrost, by definition, is soil that stays frozen year-round. But the top layer, 1 to 3 meters thick, thaws every summer and refreezes every winter, the active layer. It is where roots grow, where water pools, where infrastructure lives. And it moves, constantly, invisibly, relentlessly. When water freezes, it expands. When it melts, it collapses. Roads on top do not settle evenly. They warp. They bulge. They crack in long, jagged patterns that mechanics can predict but cannot prevent. A frozen defiance. The original Qinghai-Tibet highway, built in the 1950s, taught China everything it needed to know about this permafrost misery. Crews repaired the same stretches every summer, sometimes twice a season. The road buckled, culverts snapped, bridges leaned, whole embankments slid downslope in slow-motion avalanches of mud in a climate still, by plateau standards, cold and predictable. Since then, plateau temperatures have risen nearly 2 degrees Celsius, almost twice the global average, warming faster than expected. The active layer thickens. Permafrost retreats downward. Ice, stable since the last glacial period, is finally beginning to melt. Every naive fix made the problem worse. Here is where the physics of a black road becomes genuinely cruel. Asphalt is dark. Dark surfaces absorb solar radiation. On the plateau, thin atmosphere and intense sun compound the problem. A black road heats to 60 degrees Celsius on summer afternoons. That heat does not stay on the surface. It conducts downward into roadbed, into soil, into ice below. A conventional highway becomes a giant thermal antenna. It gathers heat from the sky, injecting it into a foundation that cannot afford to warm a single degree. Beneath the asphalt, ice lenses, thin sheets of frozen water begin to melt. Voids open below. The road sinks into them. When winter returns, water refreezes and shoves the pavement violently back up. Season after season, this thermal cycle grinds fresh pavement into loose gravel, defeating every conventional highway engineer sent here. The Soviet Union learned this the hard way in Siberia. The Americans learned it in Alaska on frozen ground. Both built long roads on permafrost, watched those roads deform, and concluded traditional embankments were the enemy. A thick insulating berm of soil placed on permafrost does not protect the ice underneath at all. It traps summer heat inside and prevents winter cold from reaching deep enough to compensate for warming. Over decades, the ice underneath melts anyway, slowly, expensively, unpredictably. Engineers realized they were building a heater. But here's the thing. Chinese engineers working on the plateau refused to accept that permafrost highways must fail. They asked a different question. What if the goal was not avoiding ice, but keeping it permanently frozen? What if the road itself could be turned into a cooling machine, a refrigerator built into the earth? The real reason the Qinghai-Tibet corridor still functions is designers stopped treating the highway as a passive surface. They started treating it as an active thermal system, a distributed refrigerator engineered into the frozen ground. The first tool in that system is deceptively simple, a sealed metal pipe standing vertically beside the road. Often painted white, inside is a small amount of ammonia or carbon dioxide. Engineers call it a thermosiphon. In winter, when air above the plateau drops below the temperature of the soil, the liquid inside evaporates. It rises as vapor, condenses at the top, and releases stored heat directly into the frigid winter atmosphere. Cooled liquid runs back down. There are no pumps, there are no moving parts, no external power required. The pipe harvests winter cold and delivers it deep into the ground, freezing the soil harder than nature could. In summer, when the air is warmer than the soil, the cycle simply stops. The pipe does nothing. It waits patiently through the warm months, ready to resume its silent work when the cold returns again. The second tool. Engineers replace ordinary embankments with layers of loose, angular crushed rock, letting air move freely through the gaps. In winter, cold, heavy air sinks into those gaps, chills the rock, and drains warmth from the soil beneath. In summer, warm air is too buoyant to penetrate, so the cold stays trapped inside the embankment. This is called a ventilated embankment, a one-way thermal valve, letting cold in, keeping heat out. Above critical curves and cuts, engineers add a third tool, awnings and sunshades blocking direct solar radiation. These canopies shield the darkest, most vulnerable pavement, keeping the road 5 to 10 degrees cooler on peak days. That difference slows the thaw. But cooling one lane is not enough. The plateau itself is not uniform. Some sections are frozen bedrock, hard as concrete, easy to build on. Others are far more treacherous. Ice-rich clays hold more than 50% water by volume, the most dangerous permafrost engineers face. When they thaw, the soil does not just soften, it liquefies like a sponge waiting to be squeezed. The real reason is simple. Engineers combine techniques in layers, matching each method to the ground beneath. Where the ground is manageable, they deploy ventilated embankments and thermosiphons together to preserve the frost. Where the ground is worst, they abandon it altogether. They elevate the road above the failing earth. Long viaducts, bridges on stilts, carry the highway above the most unstable, ice-rich zones below. Pillars sink deep into bedrock or into columns of artificially frozen soil, anchoring the entire structure. Underneath, the natural permafrost is left undisturbed, shaded by the deck and ventilated by wind on all sides. Where a viaduct is impossible, engineers bury thick sheets of extruded polystyrene insulation directly beneath the roadbed. This slows the downward flow of summer heat, protecting the frozen ground from the sun above. Between the insulation and the surface, light-colored aggregates reflect sunlight instead of absorbing it. Every centimeter of this road is a deliberate choice, made from ground surveys, satellite imagery and thermal modeling. And the road watches itself. Along the Qinghai-Tibet corridor, thousands of buried sensors record ground temperature at multiple depths. Every few hundred meters, day and night, this data streams to control centers in Xining and Golmud. Engineers feed it into machine learning models that predict where the thaw will accelerate, which season, which kilometer, which lane. Maintenance crews are stationed roughly every 50 kilometers, ready to intervene before a defect becomes a failure. The cost is enormous. A kilometer of permafrost highway costs on average 10 times more than stable ground. Maintenance costs can be higher still. But the alternative, a corridor that fails every summer, is unthinkable. One stretch tests everything at once. That stretch is the Qinghai-Yushu Expressway, opened to traffic in summer 2017. It runs 635 kilometers across some of the most continuous permafrost on the planet. It is the highest expressway in the world, crossing mountain passes above 4,800 meters elevation. Between Qinghai and Yushu, drivers pass long fields of white pipes standing in rows beside the road. From orbit, satellites detect the geometric pattern of thousands of thermosiphons, arranged like a metal wheat field. Beneath them, sensor data confirms soil temperatures remain below zero even in mid-July, when air rises above freezing. Before this expressway existed, the drive from Qinghai to Yushu took roughly 12 hours across a battered two-lane road. That old road closed for weeks each spring. Now the same trip takes only 8 hours through the mountains. Trucks now move medical supplies, cement, solar panels and food. Ambulances reach remote villages once impossible to save. A decade ago, help could not arrive in time. The economic and social effects along the route are visible. The engineering effects are more subtle. Nearly a decade in, monitoring shows most segments have remained remarkably stable. Only isolated areas required intervention. Previous roads deformed within 2 years. This quiet endurance is a miracle. Yet the plateau is warming faster than models predicted. And that is the uncomfortable part of this story. The same climate change that made these engineering solutions necessary is also making them harder to sustain long-term. Studies estimate up to 40% of shallow permafrost across the plateau could disappear by century's end, even under moderate emissions scenarios. Some regions have already lost their permanent frost entirely to warmer temperatures. The thermosiphons only work when winters remain cold enough. Ventilated embankments need seasonal cold air to circulate. Every hedge that engineers built into the road assumes a climate that is quietly slipping away from them. So they keep adjusting. They add more pipes. They deepen the insulation across the most vulnerable road sections. They test hybrid systems, thermosiphons combined with solar-powered chillers that could act even during warmer winters ahead. The real answer to the paradox is now clear. The Tibetan highway is not a road resting on ice. It is a machine that keeps ice frozen, combining geopolitics, physics and climate hedging into one distributed device. Hundreds of kilometers long, it quietly transfers heat from the ground to the sky, an active thermal engine. The blueprint developed here is already being studied by engineers in Arctic Russia, Canada, Alaska and Norway. Anywhere permafrost meets the ambition of modern infrastructure, Chinese engineering has quietly rewritten what a highway can be. What they proved more than anything is that a highway does not have to be passive at all. Roads, railways, pipelines and airports can now be designed as active thermal systems in a warming world. Ground engineering is no longer just construction. It has become climate adaptation deployed at true industrial scale. The next test of this doctrine is already under construction, farther south, cutting through the eastern plateau. There, engineers are laying tracks of the Sichuan-Tibet Railway, the most difficult infrastructure ever attempted on land. Where the Qinghai-Tibet line ran along a stable corridor, this new line dives through a chaos of faults. It threads deep valleys and living glaciers, with more than 80% of its length inside bridges and tunnels. Some tunnels are being driven directly beneath active ice bodies, where rock temperature shifts by tens of degrees. The permafrost challenge here is joined by geothermal heat, sudden rock bursts, and torrents of glacial meltwater underground. Every technique invented on the Qinghai-Yushu Expressway is now being pushed harder, tested at absolute physical extremes. The maintenance fleets patrolling this new line are being redesigned as well. Prototypes of hydrogen-fueled snow removers begin trials. At high altitude, diesel engines lose power and combustion turns inefficient, a fundamental problem hydrogen fuel may finally solve. Sensor networks along the new railway will be denser than anything deployed before, feeding continuous data into artificial intelligence systems. These systems anticipate failure zones weeks in advance, watching for the first faint tremor beneath the shifting permafrost crust. And still, one question hangs over everything. Will warming outpace engineering? Will climate move faster than crews can compensate? No one on the plateau claims certainty. But projects continue because retreat has never been part of the plan. The plateau has become a laboratory for future mega-projects, lessons learned above the clouds shaping how humanity builds now. In a world where the ground itself is no longer solid, one project may rewrite what infrastructure means. If these engineering choices surprised you, the channel has more films about humanity rebuilding its relationship with the physical world. Bridges that breathe, tunnels that heal themselves, and structures that outlive the very climates they were designed for. The story of the Sichuan-Tibet Railway is already in production, glaciers, faults and the highest tunnels ever attempted. Subscribe to continue exploring more stories about how our world is being